Hi everyone, it's Jakub speaking, unfortunately in this virtual setting this year, but I do hope that we can meet in person in 2021. So today I'll be talking about analyzing and trying to extract some value from multi and hyperspectral images without any ground truth datasets. So we don't have any labeled datasets, but we still want to benefit from high dimensional data that might be captured, for instance, on board an imaging satellite. As a very short introduction, I think that we all know that when we capture a hyperspectral image, we have a big number of images captured for every single wavelength, so we have a data cube that's being analyzed in the next step of the pipeline. And we all know that it is difficult to visualize, analyze, and interpret, so it is also super costly to transfer because of its volume, and those are the reasons why we don't have a big number of datasets that might be used for training in our supervised way. So here's the example from the state-of-the-art. Two datasets with labels. We can observe that although we have the labels, they are very generic and they might not be easily transferable to emerging use cases that are usually more specific. So a bit unusual, but we can conclude that we definitely need some approaches to deal with lacking ground truth datasets because we just don't have that kind of data. And of course, we can first try to synthesize the data based on the original data. If we have some data in the data augmentation process, then we can try to build our models over the existing data and then transfer it to our new domains in the transfer learning approach. We can try to generate new ground truth, and we can try to benefit from unsupervised learning where we just don't have any labels available. As I mentioned, we are interested in extracting value from that kind of data, and usually segmentation or classification is not the final but the initial step of the pipeline. And in this example, we are interested in finding the forest, non-forest pixels in the image, and then we are quantifying the area of the forest so that we can track the area of the forest in the following years, 2017, 18, 19, and based on that information we can try to infer the conclusion about what was happening in this part of the globe. If the area was decreasing, something wrong probably was happening. In our case, we've been trying to benefit from deep learning, so we proposed a very generic architecture which is encoder-decoder based. We can use any autoencoders in this architecture. Here we use recurrent neural nets. We extract the latent representation of the data, perform clustering to find the coherent regions of the image that's incoming to the pipeline. As I mentioned, it's very generic, so we can benefit from 3D convolutional autoencoders as well, or any kind of autoencoders might be plugged into this architecture. Here's the examples of the results. Over the benchmarks, we can observe that the recurrent neural nets are the best for the latent representation, and we can observe that the segmentation is pretty accurate, so we can definitely benefit from it in the entire processing pipeline. For instance, in the forest monitoring, as I mentioned, we are interested in quantifying the area, and then we can try to understand what was the change of this area in the following years or months. Another example is from the precision agriculture. We have a scene captured in Australia, and we have a very limited number of ground truth points, but still we can segment the image and we can try to understand what was happening in the points where we do have some ground truth data. We can also try to find the similar regions in other parts of the image to better understand what is being captured, what is actually happening in this part of the image. As a small sneak peek, I wanted to say a few words about the noise injection into the hyperspectral images, because we are interested in understanding how robust are the models against the noise, and we were injecting the noise of different distributions, maybe the Gaussian or impulsive noise or any other kind of noise might be injected into the original data. Then we train the model, in this case the supervised way, and then we can try to understand how robust is this model against noise. We can observe that if the noise is very aggressive, we can deteriorate the accuracy of the model and the quality of the segmentation is dropping. So we need to be aware that that is a real life problem and we need to tackle it as well. So to conclude, we can benefit from unsupervised learning to get better segmentation, to get better value from our data. We can try to extract some useful knowledge about what we can have in the image, but we need to be aware that noise might be affecting our segmentation in a very dramatic way, so we need to tackle this problem as well. Thank you for watching. I'm happy to take questions.